Hi friends, welcome to my channel VLSI Gyan. This is Sirisha, and in this session we will see what is timing closure in VLSI. Friends, we many times come across the word timing closure. So in today's session we will see in detail what is timing closure and what are the components of timing closure and the timing constraint, timing analysis, everything related to timing closure. So let's get started. What is timing closure? Timing closure in VLSI is the process of ensuring that the digital circuit meet all the required timing constraints. We have different timing constraints like maximum operating frequency, setup time, hold time, clock skew, and all different types of constraints are there. So the main aim of the timing closure is that the chip's speed. It determines the chip's speed by satisfying the timing constraints for a smoother chip operation. Timing closure is nothing but the layout of the chip must satisfy two constraints. One is geometric constraints and the second one is timing constraints. Constraints are nothing but these are the instructions which the designer gives to the system at different stages. Like we have logical synthesis, then we have timing constraints, then we have place and route constraints. So the constraints are nothing but the instruction that the designer gives to the system for proper functioning of the chip. So here basically we can say that timing closure must satisfy these two constraints. Then only we can say that the chip has completed the timing analysis or closure. So these two are geometric constraints and timing constraints. So let us see what comes under the geometric constraints. So friends, the geometric constraints are used to control the physical placement and routing of the components in the IC. These are related to the physical placement and routing of the components. So, designers rely on the EDA tools like electronic design automation tools that consider these constraints, these geometric constraints to perform place and route optimization and timing analysis. By adhering to these constraints, we can say that the timing closure can be achieved. So here the main geometric constraints used in the timing closure are minimum and the maximum wire length. The first one is the minimum and the wire maximum lengths. So the minimum and the max wire lengths are nothing but it defines the acceptable range for the wire length for interconnections. So we have different interconnections. So for that, the wire length should be in the acceptable range. If we use shorter length, that minimizes the propagation delay. Thereby, you can increase the speed of operation. Second is metal layer assignment. IC designs have typically multiple metal layers for routing signals. Each metal layer has its own characteristics such as resistance, capacitance, propagation delay, etc. Geometric constraints dictate which metal layer can be used for routing specific signals. Third is the routing space and width. These constraints help to prevent signal interference and crosstalk. So that is nothing but it provides proper spacing between wires so that there is no interference or crosstalk. The next is the area and the aspect ratio. The area and the aspect ratio allows area and aspect ratio for certain circuit component or block. It deals with the size and shape of the critical elements. Alignment and symmetry constraints, placing specific circuit components to ensure balanced signal path to minimize the skew. We know what is skew. Skew is nothing but the difference in the arrival time of the clock So many times this happens when you have not proper balanced skew. So alignment and symmetry constraints. Then we have clock tree constraints. Geometric constraints govern the placement and routing of the clock tree, ensuring balanced clock distribution, controlled clock skew. So these are some of the geometric constraints which we have. And next, let us go to the other type of the constraint, that is timing constraints. Timing constraints plays a very important role. So out of that, we have our main constraints listed over here. There are many other constraints also, but a few are listed over here. Timing constraints play a crucial role in ensuring proper operation and performance of digital circuits, such as setup time, hold time, propagation delay, clock skew, false path, and multi-cycle path. Friends, in my previous video, I have explained what is setup time, what is hold time, and clock skew. If you are not familiar with this term, I will provide the description in the description box, the link of this videos. Please do watch and get the concept clear. So friends, these are some of the constraints which we use in our timing constraints. So let us see one by one what they are and how they affect the timing closure. So friends, sorry, timing analysis and timing constraints are closely related and interdependent aspects of the design process in VLSI. Timing analysis is nothing but the process of evaluating and verifying the timing behavior of the digital circuit to ensure that it meets the required timing constraints. Means we are checking whether the timing constraints are met or not using the timing analysis. So these two are interrelated. So basically, timing analysis is again divided into two types. The first one is the dynamic timing analysis, and the second one is the static timing analysis. So what is the difference between these two? Dynamic timing analysis or simulation guarantees 100% coverage. It guarantees our 100% coverage. It is design specific. One method cannot be used to all designs. It is design specific means you cannot use the same test bench or the same method to the other one. You have to use a different method approach for every analysis. Hence, for each design, a unit test bench need to be created. Generalized approach is required so that verification process is speeded up. So these are some of the features of the dynamic analysis, timing analysis. Next comes the static timing analysis. The static timing analysis is very popular method of timing analysis in VLSI, and it is an approach in which no inputs are required. Here we don't give any input vectors. Input vectors are not required. Input is not required. And it is a general approach which can be applied to any design irrespective of the criteria. Any design can be used. We can use any design for the static timing analysis. Design is considered as a collection of groups or path. So it sees the design as a collection of groups and paths. It does not go into checking the functionality of the design. Whereas in the dynamic, we have the functionalities also checked. Whereas in static timing analysis, the functionality of the paths are not checked. Okay. Then the path which satisfies its timing requirement cannot offer timing violation. Once the path is satisfying the timing requirement, cannot offer timing violations. Importance given to logical levels rather than logical values. Logical levels are given more importance rather than logical values. So what comes under the static timing analysis? So first one is the setup time and hold time. So the first constraints which is very important is setup time, and the other one is hold time. Setup time and hold time. So what are these? Setup time is the minimum amount of time the input signal must be stable before the active edge of the clock. Means suppose you are applying a clock. So before the application of the clock, before the clock's active edge is there, your data must remain stable. So the data must be stable before the active. This is the part where your clock is changing with active edge of the clock. So before that, a certain duration of time, your data has to remain stable. So this is called the setup time. Otherwise, what will happen? If the data is not stable before the active edge of the time clock, there are the chances that incorrect data may get propagated throughout the circuit. The capture flop may catch a incorrect data. So to avoid that, the data must be stable before the active edge of the clock. Similarly, what is hold time? Hold time is the amount of time the input must be stable after the active edge of the clock. After the clock is active, after that again, the data is not supposed to change. It should remain stable for some time, and this duration is called hold time. So the data must remain stable before and after the active edge of the clock. These are the setup and hold time constraints. If the data is not stable during this window, there is a chances of metastability. Metastability is a condition in which the output is unpredictable. It remains in a state which is not predicted, which is not the correct state. So to avoid that, what is required is that we must not violate the setup and hold time constraints. Next, in another diagram, we'll try to understand in much more detail about this. We can see that here we have again the same thing. Your clock is going from low to high. This is the low to high. Here from active edge, this is the active edge of the clock. And your data, this is the data. Whatever the values are changing, the data can change, but this portion should remain stable. In this portion, it must remain stable. During this time period, it must remain stable. This is called setup time. Similarly, after the clock hits, the data must remain stable for this much duration. And what is this time? This is called hold time. And after that, it is allowed to change. So before setup time, it can change. After hold time, it can change. But during the setup and hold time windows, the data is not allowed to change. It has to remain stable in order to avoid metastability. If metastability occurs, there are the chances of getting errors, timing errors, or getting the improper output. So to avoid that, setup and hold time must not be violated. Next comes the clock skew. Clock skew is the difference in the arrival times of the clock signal at different locations in the circuit. The clock is generated from the same source, but it is not necessary that it will reach to all the parts at the same time. So there are the chances that the clock for one flop is arriving at one time and the other is receiving at another time. So the difference in the arrival time of the clock is called skew. Skew is nothing but the difference in the arrival time. So this is the type of the skew. Is another type of the constraints which we have in our timing analysis. So here clock is skew is of two types. One is the positive skew and the other one is the negative skew. Positive skew occurs when the signal arrives later, when the clock signal arrives later at the destination compared to its reference source point, reference of the source point. So the data clock signal is arriving later. It is late. So that is called positive skew. But when the clock signal is arriving earlier, then time it is called as the negative skew. So here in positive skew is nothing but that the destination point experience a delayed clock arrival. The clock is arrived at a delayed time compared to the source. Positive skews are mainly because of the variation in the wire length, differences in the circuit components, or unequal delays along the clock distribution path. And negative skew, what happens is here the destination point experiences an advanced clock. The clock is arriving earlier than expected. And this is also because of the variation in the wire lengths, difference in the circuit components, or unequal delays along the clock distribution path. The causes are both the same. So the clock may come earlier or may come later. So if it is coming earlier, then it is called negative skew. If it is coming later, then it is called positive skew. Next timing constraint is propagation delay. Propagation delay in VLSI refers to the time it takes for a signal to propagate through a circuit from its input to output. You are applying an input to the circuit, you are getting an output. So the moment you are applying the input, you are not receiving the output. There is some delay, and this delay in VLSI is called propagation delay. This delay is mainly because of capacitance and resistance of the interconnect, gate delays, and the driving capability of the transistor. Here we can see a simple example, which is of a AND gate. It has the two inputs, I1 and I2, and it has an output O. So the moment you are applying the inputs, you are not getting the output. There is a delay. There is a delay, and after that delay, the output is obtained. This is called propagation delay. Next constraint is a false path. False paths are the paths that physically exist in the design. They are physically present in the design, but are not logic or functional path. Means we are not, the designer doesn't want that part to be sensitized for the timing analysis. So these paths never get sensitized under any input conditions. So some of the examples of this design are, like you can see here, two mux are there, mux 0 and mux 1. Two mux 1, 0 and 1. And these are all both 2:1 mux, two input lines and one output line. The output of first mux is given to a combinational circuit, and then it is given to the second mux. You can see that the select line of both the muxes are tied together and they are given a common input select. Okay. So what happens is when first input is selected, suppose, so there is a path called the output of this is connected to the input of first, but this is impossible because both the select lines are commonly tied together. So they both will, if suppose S is select is 0, select is 0, that means the input 1 is selected for both the mugs. So when this is selected, so there is no such path like this. There is only one path like this. There is no physical path like this. So this path is called a false path. Next comes the multi-cycle paths. Multi-cycle paths are the paths which intentionally require more than one clock cycle to propagate. This information cannot be possibly inferred by the timing analyzer. So the designer has to specify the path, and he has to mention the timing compute. He has to compute the timing also. Like you can see in the figure given below. You can see here there is a register A and register B. And between these two, you have some combinational circuit and it takes a multi-cycle path. This is our multi-cycle path from register A to register B. So it is like in general, what happens is that at the moment you are applying the input in the next clock cycle, it should be received by the next register. But in multi-cycle paths, it takes more than one clock cycle to propagate. So this is how we'll see. So the same previous figure I have taken here. You can see register A, register B. Between these two, we have a multi-cycle path. So in general, the source clock is there. So the destination clock, the hold edge is the same. There is no change in the hold edge. But the setup edge, you can see that is the next clock for the normal one. But when you are applying the enable based constraint, then that time, if it is taking two clock cycles. So here, the setup edge will shift to two clock cycles. So the same we can mention here, the set multi-cycle path to set up from reg A to reg B. Set multi-cycle path 1 from hold from reg A to reg B, because hold is not changing. So hold is the same 1 and setup is 2. So this is about the multi-cycle path. Next is how we can go for a better timing analysis, how we can use advanced synthesis constructs for better timing analysis. Advanced synthesis constructs are those constructs which are synthesizable. We have different types of synthesis constructs like fully synthesizable constructs, partially synthesizable constructs, and not at all, no synthesized or non-synthesizable constructs. So here, if we go for advanced synthesis construct for better timing, then we can have different types of approaches like synchronous and asynchronous pipelines, clock gating, then clock domain constructs, and we have false path constructs and advanced clock constructs. So in advanced synthesis constructs, we have the different techniques like synchronous and asynchronous pipelines, clock gating, clock domain crossing constructs, false path constructs, advanced clock constructs. So let us see one by one, and there are other techniques also. So I have listed a few. So let us see in detail what these are. So the first one is synchronous and asynchronous pipelines. These introduces additional pipeline stages in the design to improve timing analysis. Pipeline stages means like the design is broken into smaller sequential stages, and the critical, by that we can reduce the critical path and we can add some pipeline process. So synchronous pipelines use the same clock, whereas asynchronous uses handshake protocol to control the flow of data between the stages without relying on the global clock. The next comes is the clock gating. Clock gating is a technique used to control the clock signal to specific circuit elements based on the certain conditions. Like clock gating is nothing but if we have many times come across of the chips like where we have the clock enable. So when what happens is it is a enable signal is there and it is controlling the clock to that particular part of the circuit. So that by that you can reduce the power. And you can increase the efficiency of the circuit. By getting the clock into inactive or idle components, power consumption can be reduced. And timing analysis can be focused on the active and the critical parts of the design. Clock gating constructs help to identify and optimize the critical timing paths more effectively. Multi-voltage design. Multi-voltage design are nothing but the voltage designs allow the different stage voltages domain within the design, and these constructs facilitate power optimization by enabling the voltage scaling in the different parts of the design. Next is the clock domain constructs are used to handle data transfer between different clock domains in a design. Like CDC is nothing but data from one clock domain is transmitted to the another clock domain. So that time we can use the synchronizers, PFOs, and other data transfer mechanisms like handshake protocols, asynchronous FIFO, and all. So that this can be, we can come across, we can overcome the effect of metastability and all. Then we have the false path constraints. So these are, as earlier we have seen, the false paths are nothing but these are the paths which are physically present, but they are not like they are not functional or logical path. So the false path constraints are utilized to exclude specific path from timing analysis. So these paths are typically non-critical or intentionally designed to not have the timing relationship that need to be met. By marking certain path as false path, the timing analysis tool can focus on the critical path instead of wasting time on the false path, reducing analysis complexity and providing more efficiency. Then we have the advanced clock constraints. So advanced clock constraints provide additional timing information about the clock signals, such as the clock uncertainty, clock skew, clock jitter, and the clock relationships. These constructs help capture more accurate timing behavior and enable better analysis of the clock related issues during the timing analysis. Some examples of advanced clock constraints are clock uncertainty, clock skew constraints, clock jitter constraint, clock relationship constraints, and clock group constraints. So friends, this is all about the timing closure. I hope that you have enjoyed the video, and please like, share, and subscribe to my channel because it provides motivation to make new videos. So if you have any doubt in VLSI, please do leave a comment in the comment section so that I will try to clarify it and I will try to make a video on that particular topic. Thank you. Thanks for watching.